Cancer is a leading cause of mortality, accounting for 1 in 6 deaths globally. It is a pathological process resulting from the accumulation of mutations in cell-mediated replication errors. Depending on the level of cellular aberrations and inducement of abnormal growth, cancer is staged in the clinic to select a treatment strategy. Treatment and outcomes differ corresponding to the clinical staging done by assessing cancer biomarkers. Due to the complexity of each cancer, treatment needs to be customized. Hence, drug combinations are frequently used in try-and-error processes to treat cancer patients to improve effectiveness and reduce the adverse side effects. However, given the variety of drug combinations, it is costly and time-consuming to experimentally screen all possible drug combinations. The advancement in technology has allowed the collection of various biological data types at an unprecedented detail level. The integration of the various omics data will help to achieve a more comprehensive understanding of the underlying biological factors, hence giving rise to a holistic molecular perspective called the multi-omics approach in cancer studies to optimize cancer treatment. Due to their inherent data variations, multi-omics data integration remains an ongoing challenge for many researchers. Another main issue is high dimensionality nature, where the datasets have a large number of predictors but low samples in relation. This complexity in today's omics data has made it difficult to be effectively managed by traditional machine learning algorithms. However, deep neural networks can handle copious amounts of complex data and model biological complexity with better accuracy. Therefore, in this study we use deep neural networks, and in particular we use feed-forward networks and 1D convolutional neural network. And in order to tackle the high dimensionality problem, we use popular dimensionality reduction techniques such as PCA, ICA, and SVD. The objective of this study is to apply DNN techniques to predict the drug responses for the selected drugs to determine the most effective drug combination. This allows doctors to take a more informed and customized approach to prescribe anti-cancer drugs that are more likely effective for cancer treatment. These are the datasets used in this study. It consists of 6 omics data and 1 drug response data. This is the project flow pipeline. The raw data is pre-processed and it undergoes dimensionality reduction using the 3 techniques mentioned before. There are 2 types of networks, feed-forward neural network and convolutional neural network. We experimented with both individual DNN and combined DNN, which will be explained in the following slides. For the individual DNN, the reduced dimension dataset is fed into the DNN model. It predicts the drug responses to the 24 drugs, and each dataset is trained individually. Since we have 6 omics datasets, 6 individual models were created for both feed-forward network and 1D CNN respectively. We experimented with both 1 and 2 hidden layer models. We mitigated the high dimensionality problem through dimensionality reduction techniques as mentioned before. To tackle the second challenge, which is the effective multi-omics data integration, we created a combined model. In the combined model, we combine the 6 individual models into an integrated model with truly multi-omics data. To attain the integrated model, we introduced an attention mechanism as inspired by the attention mechanism used in RNN, with the aim of discovering the significant omics that contribute more to the drug response levels. The figure represents the model architecture of the combined DNN. We compared the performance of dimensionality reduction techniques based on the combined DNN results. As we can see from the results, PCA performs the best as it has the lowest MSE value compared to the other 2 techniques. Therefore, we concluded that the PCA is the best performing dimensionality reduction technique for this study. For the performance of individual DNN, we observed that the 1 hidden layer feed-forward network performed better than the 2 hidden layer feed-forward network, and the 2 hidden layer 1D CNN performed better than the 1 hidden layer 1D CNN. We evaluated the models based on MSE, R-square and standard deviation. Based on the performance of the combined DNN, we can observe that the 2 hidden layer 1D CNN outperform the 1 hidden layer feed-forward network on the basis of better MSE and better R-square values. For the accuracy rate of the models, we computed the rate at which the most effective drug predicted by our models were actually the most recommended drug for the specific cancer cell line. The top 1 and top 3 accuracy represents the drug predictions as the rate at which the true drug was predicted by our methods as the topmost drug and within the top 3 drugs respectively. As there are a total of 24 drugs whose IC50 values were predicted, the probability of randomly choosing one of the drugs that turns out to be the most effective is only 4%. In comparison to that, our models performed relatively well as our CNN model was able to achieve an accuracy of 96%. In this study, we explored deep learning approaches for predicting drug responses from multi-omics features. We incorporated dimensionality reduction techniques and developed DNN models that address dimension challenges. PC was able to reduce dimensions without much information loss, and combined DNN effectively integrated the complex multi-omics data as seen by the results. One potential area for future study is the joint dimensionality reduction techniques. With that, we have come to the end of the video presentation. Thank you!